morning. We begin lecture 38. Our goal is to get a good understanding of capacity. We have already made some inroads into understanding capacity in terms of the situations when information regarding the channel state is available at the receiver. Today we will complete that discussion and also look at the optimum approaches when the information regarding the channel state is available at the transmitter as well. So the goal of today's lecture will be to cover our, reinforce our understanding of ergodic capacity. How do we achieve capacity? What are the ways in which we can achieve capacity if the information is known at the receiver, and then what happens if it's known at the transmitter? So to set the stage, let me just quickly review some slides from yesterday. Again, because of there was a few questions after the lecture. I just want to make sure that the information is clarified, and also we have a good starting point for today's lecture. We start off with our understanding of capacity as defined by Shannon for AWGN channels. And that capacity is given by B times logarithm base 2 of 1 plus SNR. And the units are bits per second. If you want to look at it in terms of normalized capacity, then it will be in bits per second per hertz. And the example that we looked at was a case where we had 3 different channel conditions, each of which producing a corresponding capacity. And we then said that the ergodic capacity or the capacity of this channel would be obtained through this summation of the capacities weighted by their appropriate probabilities, and we got a expression for the ergodic capacity. Subsequently, we did a brief discussion on Jensen's inequality, which basically said that a function, expected value of a function, of a concave function of a random variable x is less than or equal to the function evaluated at the expected value of the random variable. And this basically translated into a result that is useful for us. It's the one that enables us to compare ergodic capacity with the capacity of an AWGN channel which has the same average SNR. Both the ergodic, the fading channel and the AWGN channel have the same average SNR. One is a situation where the capacity is constantly fluctuating. The other one is a channel where for the average SNR you get a fixed number as the capacity. So given these two, we find that the ergodic capacity is less than the capacity of the corresponding AWGN channel. Then we said that there are 3 cases that we can study in the context of computing capacity. First one where we know only the PDF of the distribution or the distribution of gamma, and this is known both to the transmitter and to the receiver. I just wanted to clarify one point that basically this turns out to be a very difficult problem. It is known for 2 special cases, and really fading channels is one of them. But in general, this is a very difficult problem that is not something that we focus on. What we have instead focused on are these 2 scenarios which are closer to practice, and CSIR and CSIT. And CSIR is the first case that we looked at. This is a situation where the receiver and the transmitter know the PDF of gamma, and the receiver knows the instantaneous channel condition gamma. Okay? We said that under this assumption, we can then look at 2 possibilities. One of computing how do you achieve ergodic capacity. So under CSIR, it is possible to achieve ergodic capacity under a set of assumptions. We will just highlight that. We will also look at a situation where we say, okay, not looking at the ergodic capacity, but I want to look at very practical realizable schemes. So I would look at capacity with outage. So that is the, and of course, the CSIT. Now, CSIR, the case 2 that we studied, the clarification or the point to be taken away is, if I say that I have CSIR and I want to achieve ergodic capacity, what is the method? The transmitter does not know what is the channel condition, so it has to transmit at a fixed rate. Okay? CSIR situation schemes, or it has to transmit at a fixed rate. However, the channel may be good, it may be bad. We don't know that ahead of time. So the way that ergodic capacity is achieved in the context of CSIR, only the receiver knows and the transmitter does not know, is that the transmitter must use very long code words. Okay? Basically, asymptotically, it could be infinitely long code words, which has to span all the channel states, the good states and the bad states. And the code words must then be designed such that even in the presence of the bad states, you can still recover the information with the very low probability of error. So this is where the catch comes, where you have very long code words. Very long code words means that there is delay, there is complexity associated with that. So therefore, yes, it is possible to talk about ergodic capacity, but it is one of those situations where we know that it can be constructed, but how do you actually do it in practice? It's a very difficult problem. So again, we just sort of make a footnote saying it's good from a concept point of view. You know what you should be achieving, but it is something that would be very difficult in practice because of the delays that would be involved. Okay. We looked at another example where there were two channels with different average SNRs and different capacities, and we distributed the powers, we kind of increased the power of one, reduced the power of the other. We came up with the following conclusion, that we should use both channels. It's advantageous to use both channels. There was a question after the class which said, should I always, even if the other channel is very bad? No, what you will find today in today's lecture is that once we start talking about outage, then if the channel becomes very bad, you may choose not to use that particular situation. So in this particular example, it was advantageous for us to use both channels. Again, keep that in mind. As much as possible, we try to use all the channels that are available. However, we will try to optimize the power allocation. That is a very important element. You don't distribute equal power, or don't go in the intuition saying that, okay, the channel with poor SNR requires more power, and that is actually not the right strategy. The right strategy would be give more power to the stronger, the channels with better SNR, so therefore we get the advantage of that. Okay. So with that background, let's just quickly summarize all the information that we have. So basically this would be a summary of the key points that we want to take forward from here. So we say that our capacity is not a fixed number, it is a function of the SNR, B times logarithm base 2 1 plus gamma, and ergodic capacity is a number which is like the expected value of the capacity. Ergodic capacity is given by B times integral 0 to infinity logarithm base 2 1 plus gamma f gamma of gamma d gamma. Now this is what we want to achieve. This is the max, this is the best that we can do under the fading channel. We know that this is going to be upper bounded by the AWGN capacity of a equivalent channel with the same average SNR. Okay. So the observations that we have made so far, observations, the first one is that SNR, the capacity is very sensitive to SNR. If SNR goes down, the capacity is going to go down. That is something that we have to be aware of. Second, it is advantageous to use all available channels. All available channels. Okay, that's what we saw in the example. All available channels. And the third point is that it is to our advantage to give more power. Give or allocate more power to channels with higher SNR. Okay, so you're kind of creating a more imbalance, but the idea is to achieve capacity, and to achieve capacity, this seems to be the direction in which the examples are pointing us. Channels with high SNR. Okay, so this is at a high level the key points that we have observed. Now, maybe a picture is very helpful for us. What is it that we are trying to do? We are trying to decide a encoder-decoder combination encoder at the transmitter, which will take my information. Let me call that as M of n. Then at the other end, I'm trying to decode the counterpart decoder such that I can recover m hat of n. Okay, this is the the channel that the encoder decoder has been studied very extensively in terms of Shannon capacity is the AWGN channel. So where it's additive noise. Okay, and what we have is a situation where there is another impairment that comes in the process. It's a multiplicative impairment, and that is the fading coefficient. Okay, so basically what we have is a situation where there is fading and then AWGN, and so for us the definition of the channel is from the output of the encoder to the input of the decoder. Okay, so this is my channel. This is the one in which the fading and all the impairments are happening. And this has a certain capacity, and I'm trying to design the encoder decoder to maximize that capacity and to reach that capacity. That's the channel that is present for us. Okay, so the problem statement for us is the design of the encoder decoder, design of encoder decoder pair decoder to achieve ergodic capacity. To achieve ergodic capacity. Okay, so that is the problem statement, and so far what we have said is if only the PDF is known, it's a very difficult problem. If the receiver knows this information, it will end up being that the encoder decoder becomes very complex, because you will have to use very long code words which can operate even under bad channel conditions and still give you good error performance. Okay, so a few more statements about, so case 1 is PDF only, that is both transmitter and receiver, PDF known at TX and RX. This is a difficult problem, we are not going to spend too much time on that. However, to mention that it is known for 2 channel types. Okay, so we know the solution for 2 channel types, but in general a very difficult problem. Okay, so our focus is on case 2, which is CSIR. CSIR, the following points need to be kept in mind. Again, it may seem a little repetitive, but important that we do not forget this. The transmitted data rate is constant. We are not varying the transmitted rate. So basically, transmitted data rate is constant. And the reason because of that is because the transmitter does not know what the current channel conditions are, is constant regardless of the instantaneous value of gamma n, regardless of gamma n. So this is a very important element. And of course the capacity achieving codes are very complex. Achieving codes are very long, because they have to be long enough to cover all the possible fading states, very long to cover all possible fading states, all the way from very bad channel conditions to very good channel conditions, possible fading states. And the minute you have long code words, that means that we are going to very long code words, well, not just very long code words. And very long code words means the impact will be in terms of the delay and in terms of the complexity, the decoding complexity. Okay, so both of these are factors that we have to keep in mind. Okay, so the code that has been designed must work at a constant rate under all channel conditions and give you a very low probability of error. Okay, so that is the CSIR situation. Okay, what we would now like to look at is the second one, where we are not trying to achieve the ergodic capacity, but we are trying to look at outage, channels with outage. So CSIR is the scenario. We are going to look at capacity with outage. With outage, the channel model is going to change slightly for this. Again, please pay close attention to this particular, the assumptions being made. So this is primarily looked at or studied in the context of slowly varying channels. Slowly varying channels. Okay, as opposed to the previous case where you were looking primarily at reasonably fast fading channels, because you must cover all possible states. Now, slowly fading channels with a specific characteristic. The characteristic is that the gamma of n, that is the instantaneous SNR, is not changing symbol to symbol. It is constant for a block of symbols. Is constant for a block of symbols. Okay, block of symbols. And then gamma changes. It's constant for a block, and then after that it changes. After that, gamma n changes to a new value, independent value. Gamma n changes to a new independent value and remains constant for a block of symbols. New independent value. It is from a particular distribution. It could be Rayleigh distribution or Ricine distribution basically, but the gamma of n. So the way to visualize it is, in practice what we see is an SNR that will change, right? That this is how gamma of n changes as a function of n in practice. But the channels that we are assuming are of this type. It is fixed for a period of time, then randomly changes to some other value, again fixed for a period. So basically it looks like it is fixed for a period of time and then randomly changes, and again it goes up and down based on that. Okay. Now the transmitter does not know what the gamma n is. It's just that this is the type of gamma n that we have. Transmitter does not know, because we have assumed only CSIR, does not know gamma of n. Okay. So the question is, how do I design my system such that I get through the data most of the time, but under some channel conditions I'm going to say I'm going to accept outage. I'm going to accept that there is going to be errors. The signal will not get through under some channel conditions. Okay. So basically this is the outage. So let us say that, you know, maybe for this particular channel condition I'm going to say, okay, I'm going to tolerate outage for really bad SNR, but all of these must go through without any errors. So basically that would be my design approach. So here is a way that you could start to think about the achieving channel capacity with outage. Again, it's very important to tie it to the channel model that we are assuming, because this is a channel which remains constant for a period of time and then randomly changes according to the distribution. Okay. So we'll go back to our example. I don't remember whether it's example 2 or 3. It's probably example 2. There are 3 SNRs. The 3 SNRs, gamma 1, gamma 2, gamma 3. I'm not sure if I have those values, but you can fill in those. The corresponding capacities, C1 was 26.2 kbps, C2 was 191.9 kbps. This one had a probability of 0.1, this one had a probability of 0.5, this one had a probability of 0.4. C3 was 251.6 kbps. Okay. So now if this is a situation where gamma 1, gamma 2, gamma 3 follow this particular pattern, randomly switching around, and I tell you that I have to design a system for zero outage. Okay. So basically if I say that the probability of outage probability of outage equal to 0. That means under all channel conditions you must get my data through. Then I must design my system for the worst case, which means that in this case the capacity that I can achieve will be 26.2 kbps, because that's the system that will be designed to transmit with gamma 1. It may be gamma 2, gamma 3, but again the system designed for gamma 1 will work, and therefore it satisfies. Okay. Now if I were to say that, okay, I am willing to forego gamma 1. So gamma 1 I am going to consider as outage. Gamma 2, gamma 3 must be transmitted without error. Now what is the throughput that I can achieve? In that case I can achieve a capacity of 191.9 kilobits. I can transmit at that rate. So but the rate received, some portion of the time it will the data will not get through. So because of the gamma 1 scenario, this will be equal to 1 minus probability of outage into C2. So probability of outage will be 0.1, because I have designed my system to work with gamma 2. If the situation is gamma 1, data will not get through, that is outage, that's 0.1 probability. The rest of the time it will go through. I am transmitting information at C2, rate C2, that's 191.2. But 0.1 probability the data will not get through. So the effective rate at the receiver will be 1 minus probability of outage into C2. That basically is 0.9 times 191.9, which is 172.7 kbps. Okay. Now if I want to get a little bit more aggressive and say, oh no, I want to see if I can get an even higher rate. So then I say gamma 1 I consider as outage, gamma 2 also as outage, gamma 3 I will assume that's the one that will get through. So that means I can transmit at 251.6 kbps, that's the rate at which I am going to transmit. But keep in mind that the probability of outage is when gamma 1 or gamma 2 occur, so that basically becomes 0.6. So the rate received, actual rate at which you are sending information, is that 0.6, with the probability of 0.6 it is an outage, so only 0.4 is going to get through. So this will be 0.4 into the capacity that we have, 251.6, which actually gives you a lower number, 100.6 kbps. Okay. So some observations. With outage you can have some advantages, because you're going to say that those bad channels I'm going to sort of remove from impacting my performance. So that is a important element that we are able to work with and to get out of our system. Okay. However, we need to be careful that we don't become too aggressive in terms of outage, because then the total throughput will get affected. Okay. So a summary of the points of capacity with outage. Capacity with outage. Just a few highlights. Okay. Basically, we decide what is gamma min, above which you want the information to get through. So data will be received correctly. Data received correctly if gamma n is greater than or equal to gamma min. Okay. And outage, which is something that we know exists because we have designed the system accordingly. This happens if the probability that gamma of n is less than gamma min. Okay. And the capacity with outage is given by because this is the assumptions are that it's a slowly varying channel and it's sort of what we call as a block fading channel. So under that we are designing the capacity with outage. So let's call this as C subscript outage, that means with outage. This is equal to 1 minus probability of outage into B logarithm base 2 1 plus gamma min. Right, because gamma min is my threshold above for which I have designed. Anything above that, the data will get through. Okay. So in a nutshell, what we have achieved with the discussions with regard to capacity with outage is that you have removed the effect of these very bad channels, and what you are left with are those channels under which you can pump a lot of the information through. And you can also visualize thinking of it as saying, okay, what happens to the data that got lost? I will retransmit, so therefore there is a reduction in my capacity. It is not the capacity number that I got for gamma 2, but it is something slightly less than that, because some parts of portions of the time the channel the system is in outage. Okay, so this is a good a point for us to sort of take to pause and say, okay, do we have a reasonable handle on capacity? Okay, yeah.
Do we have the information of the probability of each state all the time?
So the question is, do we know the probability of each of the states? The assumption is that the PDF is known. So yes, you do have the probability of the different states. So, because that is very important for us to decide where you want to draw the threshold for outage. Because you don't want to, like for example, in the example that we looked at, if I set the threshold at gamma 3, for example, actually it hurt me, because gamma 2 has high probability of occurring, and therefore it will actually hurt me to choose that. So yes, you must know the PDF so that you can draw the line appropriately. Okay, good question. Okay, so this is a way for us to understand what is one way of achieving capacity in a practical system where we allow outage to occur. Now the key information is now what happens if we move from CSIR to CSIT. Okay, we move from CSIR. That means the information is also known to the transmitter. So here is the scenario that we have. So encoder, okay, and then as we have drawn before, the alpha of n is present. That's the fading. The noise AWGN, and then at this point there is a decoder. So I will call it as the receiver slash decoder. Okay, this is also encoder plus transmitter. Okay, now one of the things that we have to do is we have to estimate alpha of n. Estimate either alpha of n or gamma of n. Okay, both are essentially the same information, because gamma of n is equal to alpha of n squared times the average SNR, okay, or ES by n naught. So average SNR multiplied by alpha squared is the instantaneous SNR, and that's what we want to estimate, and this is what we want to feed back to the transmitter. So basically the feedback channel is what we have here. Okay, now why didn't I draw the line all the way through? Because encoder, so what are some of the things that the encoder will change if it knows what the channel conditions are? What are the things that it will change? It will change the rate that is captured inside the encoder. The other thing that it can change is the amount of power that is allocated. So that is why I have an additional block here. So let me call this as power allocation. how much power you allocate, right? Because the transmitter now knows how much the channel is conducted, so that you can take advantage of in the channel. So this is what we would have. Okay. Now this feedback information is also needs to be given to the power allocation, because the channel SNR is going to determine how much power you're going to allocate. Where is my channel? Channel, like before, is encaptured between this. So there is feedback. I can change the coding. I can change the power allocation, that is for that particular transmission, and then this is the scenario in which we are going to achieve this information. Okay, so here are the assumptions that we make, and so the assumptions are that both Tx and Rx, they know both alpha of n and they know the PDF of alpha of n, both of which are known, and this is known through the feedback. And we also assume that CSI at the transmitter, that is CSIT, that information is perfect. That means there is no error in estimation, there is no error in the feedback channel. It's perfect and it's instantaneous. That means the information that you have is valid for that time that you are doing the transmission. Okay. Basically, if this is the framework that under which we are assuming, then here are the possible options that the transmitter can do if it notices that there is a bad channel. Okay. So if you now look at the situation of a poor channel or a bad channel, here are the options that the transmitter can do. Option 1, it can fix the rate. That means don't change the encoder or the decoder, but it can increase the power of transmission. That is the power allocation, so that you can see whether the rate will go through. Or it can go for option 2, where you fix the power, don't adjust the power, but you reduce the rate. That means reduce the information rate. Okay, so put more coding on that. So basically put more coding, therefore the likelihood of the channel. Option 3, I can increase the power and reduce the rate. I can do these 3 options. Of course, there is an option 4 where I can choose not to transmit. Okay, 4 possible options are present. Now, the key thing to note is that since the transmitter knows what the channel conditions are and it knows what are its options in terms of coding and decoding, it can choose not to transmit at certain points of time, and therefore save power and therefore achieve better performance. Okay, basically we transmit only when channel conditions are good. Tx sends only when channel conditions are good, or when it can ensure that the transmission will get through. Only when channel conditions are good. Okay. Again, that's a qualitative statement, but it's very important that we quantify it in a rigorous manner. When the channel conditions are good. Okay, let's quickly move into the aspects of CSIT, and then we will. So, one of the things that we will like to do is, we know that the SNR which occurs in the channel has got a certain distribution F gamma of gamma. Okay. Now, for each of those SNR scenarios, we can then come up with a corresponding power allocation. So just like we have, whenever for a particular gamma, we can say that, okay, the power allocation is going to be based on, is it going to be some function of gamma. Good SNR, more power, bad SNR, less power, some rule you're going to follow. But this cannot be something that is arbitrary, so you must have a power constraint. the power constraint is very important for us to keep in mind, because only then we can have a fair comparison between different schemes. This basically says 0 to infinity P of gamma. Okay, that's the power that you allocate based on the probability F gamma of gamma, D gamma. That means for all the possible SNR states, you will allocate some kind of power, and this, when you take it with the appropriate probabilities, must be less than or equal to some average power level. Okay, you cannot exceed average power level. So basically, you cannot keep adding more and more power on for some channel. Somewhere your P bar will get exceeded if you don't allocate correctly. Okay. So this is a very, very important element. We do have an average power constraint. Only then we can compare with AWGN type channels. We can compare with all of the other scenarios that, because see, this power allocation is now coming in the context of CSIT. So we should not lose sight of that. Now this can actually be written in a more effective form, which can be expressed as follows: 0 to infinity P of gamma divided by P bar F gamma of gamma D gamma less than or equal to 1. It's a very nice constraint. So basically what it says is, don't look at P of gamma as an independent quantity, look at it as a scaled number. Okay? Now P gamma of by P bar can be greater than 1 or less than 1. But at the end of the day, when you look at all the PDF of gammas, this should be upper bounded by 1. You cannot basically have a gain in power. So you have to adjust your normalized power to satisfy this constraint. Okay. So now comes the problem statement of CSIT. The problem statement was posed by Wolfowitz 1964, where he was looking at the capacity of a time varying channel, which is exactly what we are looking at, where the transmitter and receiver know the PDF, and the channel assumes that you can get both the transmitter and know the instantaneous SNR. Okay. So the assumptions, or the problem statement of Wolfowitz was as follows. He said that the channel takes on a finite set of SNRs, takes a finite set of states. Again, it's a simplified model before we attack the key problem. Takes on a finite set of states. That is the SNRs with SNR alpha gamma I. So gamma I can take a finite set of values with probability with known probabilities. Okay, and basically we would now like to compute the we have been using P for power, so I just need to be a little bit careful with this. So with known probability, let me put lowercase p of I. Okay. Basically the capacity that we are interested in is the summation over I Ci Pi. Basically this looks like the ergodic capacity, where Ci is equal to b times logarithm base 2 1 plus gamma I. Okay. Basically this is the ergodic capacity. We are going to assume the block fading model. The block fading model is what we are going to assume. Okay. Basically what we are saying is that you know what the SNR that is occurring in the channel. We have no control over the alpha, what happens in the channel, but we can, by allocating power, we can adjust the SNR of the effective channel. Okay. So basically by varying power allocation, by varying the power allocation, power allocation, what we would like to do is you can impact the SNR. You can change the effective SNR because that's going to come into play. Okay? So, but there is a fixed P average, P bar. We cannot exceed P bar. And in some cases, there may be a P max also. P max also. So, which means that you cannot suddenly apply a very large amount of power. So, basically there may be constraints, definitely there is a constraint on P bar, there may be a constraint on P max also. Again, for now we will assume that our allocations are reasonable, so therefore P bar is sufficient for us. Okay. So, the power constraint, as we have already mentioned, power constraint is integral 0 to infinity the power that is assigned f gamma of gamma d gamma divided by P bar is less than or equal to 1. Okay. Now comes the problem statement that is very, very important. So the problem that Wolfowitz was trying to address was the fading channel capacity, CSIT scenario with average power constraint, is the following problem statement. The capacity where you are allowed to choose the power allocation such that the capacity is maximized. So, the capacity is maximized over all possible power allocations P of gamma. You are allowed to choose any allocation you want, you are allowed to do, provided you satisfy the power constraint, integral 0 to infinity P of gamma divided by P bar f gamma of gamma d gamma is less than or equal to 1. That is the power constraint. You can choose any power allocation scheme is allowed and the reason you choose that is so that we can maximize the capacity B times integral 0 to infinity logarithm base 2 1 plus gamma f gamma of gamma d gamma. I have left a little space there because gamma was the SNR that the channel gave you, but you modified it using power allocation. So, the power allocation that you are doing is P of gamma divided by P bar, very important. Okay. So, basically that is a number that can be less than 1, greater than 1. So, which means that it will affect gamma, and because you have done this power allocation, it will result in a certain capacity and you are allowed to maximize. You can try all combinations of power allocations such that you can satisfy and you can get the capacity. Okay. Let us call this as A. Now, the question is, do we know an answer for this particular type of problem statement? And it turns out that yes, we do have an answer for this in a very, very intuitive and very satisfying manner. So, here is the solution to this particular problem, and I will leave you with, to think about that. Okay. What we are going to do is, since there is a finite number of gammas, so basically for each gamma j, design an encoder decoder pair. Design the encoder decoder pair. Okay, and you also have the option of adjusting the power allocation. So, basically the power allocation for gamma j, power allocation will be P of gamma j divided by P bar. Okay, that will be the power allocation. So, here is what the model is going to do. it's going to design, let's say there are gamma 1 through gamma n, there are n states. Here is the gamma 1 encoder, gamma 2 encoder, this is gamma n encoder. Okay. Each of these will get power allocation, and that power allocation, when you look at it in terms of amplitude, this will be square root of gamma 1 divided by p bar. This will be square root of p of gamma n divided by p bar. That's an amplitude scaling. When you take the power, you will get the appropriate SNR scaling. And here we have just a multiplexing switch. Okay. This goes into the channel. Channel will give you the multiplicative factor alpha of n, the additive noise eta of n, and at the receiver I have a simple demultiplexing switch which says this is gamma 1 decoder all the way to gamma n decoder. Okay. And what am I feeding back? I am feeding back what is gamma n. Okay. So this is, and where is my channel? Channel is still the same. Notice it's a very elegant design which says if I have a finite set of gammas, I must find out what is the optimum power allocation. That is, I have not yet solved that problem. Once I have solved that problem, then the realization of the capacity becomes fairly elegant and simple, where we say that, okay, design the optimum encoders, encoder-decoder pairs, apply the appropriate power allocation, and then all you need to do is estimate what is the current channel conditions. You transmit using that particular encoder, and at the other end, using the same information, you make sure that you pass it through the appropriate decoder and you achieve the type of. So this is a very good way to understand. Now the key point that we now have to address is how do I do the power allocation? Okay, so basically the question now then goes down to how to do the power allocation. That's a very, very important problem, and we now have to pose the question in the following manner. Okay, so here is the problem statement, and we will then solve it in the next class. So now what are we saying? That we now have define a objective function. The objective function, we'll call it as J. It is based on the power allocation P of gamma and the Lagrangian variable lambda, such that you want to look at the maximization of this particular quantity, 0 to infinity b times log base 2 p of gamma by p bar into gamma 1 plus f gamma of gamma d gamma. That's the objective function. That's what I want to maximize, subject to a power constraint. So minus lambda times integral 0 to infinity p gamma by p bar f gamma of gamma d gamma minus 1. Okay, or if you write it as p gamma f gamma of gamma d gamma, it will be minus p bar. Okay, so basically this is the objective function. This is what we need to work with, and basically we want to find out that optimum power allocation that will give me the desired result. So think about this. once you know the power allocation, you know how to achieve the optimum capacity. Now the key, last step is how do you find out the optimum power allocation? And this is very important for us because this may turn out to be a somewhat counterintuitive final result, but it will also tell us how to achieve the capacity of a telephone line channel. Okay, thank you.